When we add the sodium to the water, it creates a transfer of electrons from the sodium to the water, which generates positively charged alkali ions that repel each other and cause a Coulomb explosion. Sodium has a high reduction potential and readily reacts with natural materials like water. It also has a low melting point because it has one of the lowest first ionization energies, and since it has a large atomic radius, the distance from the electrons in the nucleus is greater, decreasing the energy required to remove the most loosely held electron.
So pretty much, since the reaction is exothermic and sodium has a low melting point, when the sodium is added, it melts, and the heat generated by the melting of the sodium combined with the production of hydrogen gas ignites the hydrogen gas and causes the flame. We used the phenolphthalein indicator to show that sodium hydroxide was produced in the reaction. The indicator turns pinkish red when in contact with sodium hydroxide.
Since sodium is an alkali metal in its natural state, every piece has slight variations in its chemical properties, resulting in variations of the reaction. In our first trial, the sodium produced more heat that ignited the hydrogen gas, causing the flame, so less sodium hydroxide was produced, resulting in the phenolphthalein only being present at the top of the beaker. The color of the flame is affected by what metal is used, so the yellow color indicates that sodium was used in the reaction.
In the second trial, less hydrogen gas was produced, so while there was no flame, the sodium hydroxide was abundant throughout the whole beaker, indicated by the dark pink color of the phenolphthalein. The piece of sodium remained in ion for much longer, showing how atoms bond together to form an ion. The ion is perfectly polar, resulting in the perfect sphere shown.